Okay, guys, so let's start. We're going to do experiment number 11. Okay, this experiment, there's no lab report. You can just complete the lab data sheet. That should be enough. Okay. The data sheet has all the post-lab question also at the very end. Okay, just type all the answers here and then upload into the Moodle. I will open this. Let's change this due date to maybe like tomorrow midnight. That should be fine, I think, right? All right. Any other question? Okay, then let's start this experiment. What we're trying to understand is the radiation and the radiation shielding and the half-life. Okay, those are the three objectives. So in terms of radiation effect, so if you take a look at the periodic table, usually all the most of the materials are stable in terms of time scale. What we generally talking about our frame of reference time scale. Okay. But there are certain type of elements you can find in the periodic table. Those certain elements are actually very unstable in nature. So those elements are releasing its mass, try to change its mass towards a stable isotope. So usually all of those elements eventually go towards the carbon. So that's when it becomes carbon or iron, it becomes more stable. So for example, if you take the uranium, which is a very radioactive element, so it's releasing energy because it actually trying to go towards a stable isotope some way. So when this radiation emitted, as various type of radiation emission can be detected. So the usually, if you go back to the electromagnetic spectrum, the very high energy radiation are the gamma rays, right? Instead of gamma rays, there are other the particles, radiation particles can be emitted out as a result of radioisotope element. Okay, so the in generally we think that background doesn't have any radiation. That's our general conception. But technically it is not. Background also has a little bit of radiation, but the high energy radiations are actually very low in our background, our environment, because all the high energy particles, radiation coming from the sun and the outside the earth, those are actually shielded because earth has a huge, very strong magnetic field around it. And we have a very dense atmosphere. All of those actually can shield us from the high energy particles coming towards the Earth. So the idea of the experiment generally now to detect the radiation, let's say, for example, I have a radioactive element. Now I would like to detect the radioactivity. Now that if you want to detect that, you have to have a certain type of measurement technique, right? So that measurement instrument we generally call the Geiger counter. So it's exactly very similar to the tube you can see on this picture right here. Exactly very similar. That is the detector, and the detector connected into right here in this small apparatus that actually can tell you how much radiation Geiger counter detected per second, per minute, or per given time. Like if you want to detect it per 30 seconds, it can tell you this many radiation is detected. Okay, that detection process in that detector is actually a completely different phenomena, because that has a gas. So when the radiation come and go into the gas particle can ionize itself. So the radiation you can't just detect without anything. So what it actually detecting how much that ionization process is happening. Okay, so that's what really the detector does. So that way it can technically detect how much radiation is actually coming and hit that detector. Okay, so that's what the Geiger counter does. So if I have a Geiger counter, which means we can just let it open to the air and then try to detect the radiation. Usually around our atmosphere, we should detect very, very small amount of radiation, okay? But then you can see later, after we switch on certain different type of radiation, then you can see the detection amount going to be like hundreds of thousands times larger than the surrounding or the atmospheric radiation. Okay, so that's the way we're going to measure that. And the other idea is that what we're trying to test is the how to shield the radiation. Like for example, if you're working in a nuclear reactor and then so on, then the radiation should be shielded, right? So that shielding can be done by using different materials. Like in this experiment, we can test it out with the at least 3 different type of material, like the cardboard, plastic, and then maybe very heavier elements such as lead. So then you will see the difference depending on how heavier the element is, then it can actually shield better, because if the element is not heavier, material is very lighter, not much dense, then that material cannot actually shield the radiation. Okay. Now, there are various methods actually that shielding can be done. We just basically try to understand whether the shielding is possible by using the heavier or denser medium or not. That's the idea. Okay. And then the next part B of the experiment is identifying the unknown material, unknown radioactive source. Now, to do that, there are various techniques available nowadays. But in this experiment, what we're going to do, we're going to test it out non-radioactive sources first, alpha, beta, and gamma, and then we're going to collect the data for the unknown radioactive source, and then we're going to compare that data with our known data, which we collected before, and then by comparing, we can get an idea about what should be the unknown radiation by just comparing how many radiation detected per second, per 30 seconds, or per 1 minute. And also later we can check how the shielding is response with the unknown radiation. By just comparing all those data, we can identify what that source should be. And the last part is actually the real experiment. If we're doing this in class setting, actually, we do another part to identify how the radiation emission is sensitive, that sensitivity changes as a function of radius. For example, let's say I have a radiation source right here, and then we all directions of that small radiation source. And so we're going to do only move our detector starting from R, like maybe 5 centimeters or so. See how the detection change as a function of R. So the detection usually tell you how many number of counts. Okay, that's what actually we're detecting. How many number of counts per 30 seconds, per minute, or per 10 seconds, and then so on. Now that part we can't do actually with simulator. Other than that, everything else we can do with the simulator as we do in the in-class setting. Okay. But overall, I think the simulator is better, because when we do this experiment in class, we have actually radiative sources. And when we use in the radioactive sources like the gamma source, for example, it's a very strong radioactive source. That's a concern always students and our perspective, because everybody worrying about the exposing to the radioactive source, right? But the in-class work, even the radioactive source we use extremely not effective at all. Generally speaking, amount of radiation emitted with those sources going to be like 1,000s of dental X-ray radiation you're going to expose. So it's almost like negligible. Okay, but it's still it's going to be affected. Okay, and that's the only part we can't do. We can't actually test it out this particular part, how the number of counts varies as a function of R. It should be the inverse square law. It should be varies. If you go further and further away, it will be rapidly decreasing, then almost negligible after certain distance. Like in our sources, in our experiment, if you go like maybe even 3 feet or even like 2 feet, generally it almost negligible. So it's going to be like very, very rapid decrement. You can, if you make a graph, it's going to be like look like that. In our particular case, we're going to put the source right here. And then if you go like maybe 2 feet, then we can see the radiation detection is actually almost negligible, almost very close to zero, like close to the background type. Okay. So that part we can't do. So the last part is actually the real experimental in terms of calculation point of view. We try to understand what is this, the idea called the half-life. So the idea of the half-life is that if I have a radioactive element, let's say some source, right? In this case, we are using barium 137, which is unstable. So if I have the barium 137, it try to reduce itself, its mass by emitting the radiation, go into the stable isotopes. Okay. Now, if I detected barium radiation, let's say when the time equals 0, we detect certain amount of radiation N0. Now, if I continuously detect that radiation, then after some time, this amount of N0 going to become N0 divided by 2. So the time it took to reduce starting N0 to N0 by 2 is actually called the radioactive half-life. Half-life means exactly the time it took to reduce amount of radioactivity into half. That's all. Now, this half-life for example, like the carbon 14, it's going to be like almost 5,400 years, right? That very, very large. And some of these very strong radioactive elements has the half-life about like maybe 30 years, 40 years, 100 years, even more than that, okay, depending on the source. That's one reason why the people use, especially like the archaeologists, those kind of people who search the historical information, those people use the method called the carbon dating to figure out how old the certain artifacts and then so on. So that's one reason, because if you can detect something, some carbon in the certain element, certain artifact, then by understanding how much the radioactivity right now in that carbon, you can actually identify how old that particular artifact is. So it's going to be very useful technique people use all the time to understand the history of certain cases. Okay. That's the general idea. Now, in terms of when we're talking about this half-life, now what we're really detecting is actually rate of change of number of counts. So we say it's count because the reason is that what the Geiger tube does, it actually detect the radiation. Radiation is completely random, right? It's a complete random event happening in that element. And when the radiation detect, it actually can't tell you anything about that radiation, but it can tell you whether it detect the radiation or not. That's all it can tell you, right? So it has an internal gas tube. Gas ionization is actually can be converted into a small voltage signal. So it can tell you this much radiation I detected per 10 seconds, per 30 seconds, per minute, and then so on. That's what it can do. That which mean we can just simply say rate of change of activity, amount of count is actually directly proportional to the number of counts. So that's what we can generally say. If you just rearrange this one, this is for average. but the same thing we can write for instantaneous, right? In terms of more calculus point of view, then you can do dn over n, which is directly proportional to dt. Now this proportionality constant I can get rid of, proportionality sign I can get rid of by putting a constant dn over n, which is equal lambda times dt. And this formula, now you can see I can integrate, right? Simply both sides. If I integrate the both sides, I can develop a small equation to understand how the radioactivity changes as a function of time. Okay, this initially, let's say, it detecting when the time is equal in 0. After some time, detection changes into, let's say, n. It no need to be necessarily half-life after any time, right? So that's why when we doing the half-life, we can't use any radioactive element, because some of the strong radioactive sources has the half-life is about like 30 years and then so on. So we can't do the experiment, right? So that's why we specially selecting this barium 137 for this experiment. Even for in-class setting, that's the source we using. The reason why we use that half-life for this one is about like 153 seconds. So that's very, very small half-life, right? So which means I can detect couple of half-life within like few minutes. So that's the idea. If I want to understand that, I need to collect the data within very short period of time, but more than one half-life. Then only I can do that observation clearly, right? This lambda is actually called the decay constant. Decay constant. So that tells you, for example, how the decaying, because this is a decaying process, right? This is a decaying process. So how the decaying process happened, that decay constant depending on the source, what we are observing. Okay, it may not be the same for every decay, every source. So that's why we have to first identify the decaying constant. And then after we identify that, we can actually calculate the half-life. That's the plan. Okay, any question? Okay, then let's go back to the theory section and then take a look. Now, if you integrate this one, this is a decaying constant. Because of that, that negative sign must be there, right? I forgot that earlier. Because it's decreasing as a function of time. If you integrate that one, you will get ln right here, because 1 over n here, right? That 1 over n integral will provide you ln. That equation you can change into the exponential. If you change that, then you will get number of counts detected as a function of time is equal n0 times e to the minus lambda t. Now, if you look at it, this equation, I can easily find it out the time constant or the half-life by using this one. Half-life means when nt is equal t half. Generally, we use tau to represent the t half, right? So this should be equal to n0 divided by 2, which is equal n0 e to the minus lambda t half right here. So n0 will cancel out. Then you can simplify that formula, right? If you simplify that formula, then you will get t half. That is actually, sometimes people write this way, t half. Sometimes we use this tau to represent the half-life. Either way, it's the same idea, okay? It's just the half-life. Half-life is just simply equal 0.693 divided by the lambda. Now, the idea is that 0.693 because you have 2 there. Okay, that's why. Now, the idea is that if I want to calculate the half-life of an element, the radioactive isotope, then I need to understand what is the decay constant of that particular radioactive isotope. Okay, that's the plan. If I have that, then I can easily actually calculate the time constant or the half-life. Now, how to do the radioactive, this decay constant? Now we can do the same way like we do for any of the radioactive element. You just put the radioactive source. Let's say in this case, barium 137. That's our radioactive source right here. Then we're gonna place the Geiger counter, that is our detector, and then Geiger counter will connect it into the count meter, and then that will tell you how many number of count per second. So if you're doing this in class, what we're going to do, we have to do like very quickly because barium 137 is not naturally available. We have to make it, right? So there's the particular component we can activate it. After we activate the barium 137 source, we can't wait too long because the half-life of the barium 137 is very, very short, like 150 seconds, right? Because of that, immediately after you activate it, what we're going to do, we're going to quickly place in front of the Geiger tube and then start counting. Now, when we're counting that, if you're doing this in class, what we're going to do, we're going to count the number of count as a function of time. So which means we need actually two people to do this. If you're doing this in class, each time one person has to observe and then tell the number like after 30 seconds. When the time is 0, tell the number like after 30 seconds. Time is 30 seconds, then tell the number, then report it other person. Then after another 30 seconds, that means 60 seconds, report it. And then 90 seconds, report it. And then 120 seconds, report it. And then so on. What we're doing actually, what we're reporting here is the total count. Because Geiger counter, we're not going to stop. We're going to put it that into a continuous mode. So which means Geiger counter will be continuously added up. So what we're really reporting here, first time it actually after 30 seconds, the number you report after 60 seconds is actually total 60-second report, okay? So that's what you actually getting if it is in-person setting. Now, if I want to really make a graph and then understand this behavior, I have to look at the formula. If you look at the formula, so the equation what we're working is actually this one, right? So if you look at it, that equation is actually e to the minus lambda times t, which is equal n over n0. You can take the ln and then rearrange this equation. I can do actually exponential fitting, nothing wrong. But the problem with the Excel, you can't do exponential fitting with the Excel because Excel has only one type of exponential fit. We can't really manipulate that with the Excel graph. Because of that, exponential fitting is not good for Excel. So we're going to linearize this fitting. If you want to linearize, you take the ln on the both sides. If you take the ln on the both sides, you will get negative lambda t, which is equal ln n minus ln n0. Then you take this into the other side, then you have formula ln n is equal minus lambda t plus ln n0. Then I can report time, that is our x-axis. We are reporting n, that is our y-axis actually. ln n, the complete one is the y-axis. Then if you make the graph ln n versus the time in second, ln n has no unit, just the number of counts, right? If you make that graph should be look like this. It has to have a negative slope and it should be linear, right? It should be look like y equal ax, negative ax plus b. Now, if I have that graph, then all I need to do is extract the slope. If I extract the slope of the graph, that slope is a is actually the lambda. That is the decay constant, right? That what we need to understand or calculate the time, half time, right? So just the 0.693 over lambda is actually the half-life. So I just need this value, slope of the graph. Not only that, if I take the y-intercept of the graph by using y-intercept, that is b, I can actually identify how much amount of count detected when the time equals 0, because the problem with that, we think that this is actually, we can use this data point as the count time equals 0, but we cannot use that idea. The reason, when you activate the barium 137, you bring that where you actually have the Geiger counter, and then within that time period, there's amount of radiation loss. Because of that, we actually don't know what is the amount of radiation exactly when we activated that. When the time is equal 0, we have no idea what is the radiation is. The only way to detect that is actually by using our graph. Okay, so both of the parameters are very important to understand the radiation source and the behavior of the radiation. And on the other hand, if you make another graph, for example, let's say total number of count versus the time, the number of count versus the time, then that should show you it should be decaying constantly, because right here when you starting t equals 0, we have the very strong radioactivity, but when the time goes on, radioactivity will be decreased because each half-life radioactivity becomes half. Then after another half-life, it becomes another half, and then so on. After some time, it's going to completely disappear. So that's a problem with this. When the disaster happened with radioactive, the strong radioactive elements like the uranium or things like that, which we use for the power plant, for example. So those elements, radioactive half-life is actually very, very large, many years. So that's the problem. Then the people can't actually go around that area or expose to themselves in that area another maybe decades or maybe few decades or even like hundreds of years. We can't really live on that area. One of the places is Chernobyl in Russia. So that's completely isolated. Still, I think it melted down, I think, somewhere in 1980s, probably, as I remember. But still it isolated. The huge radioactivity is still there. I think nobody can't reach the place still. So it's prohibited region, and then so on. And the Japan, the recent one also, I think, is still isolated after that incident happened. So we are lucky in terms of that angle because we have many the nuclear power plants around us, but we are in very luck situation. In that kind of situation never happened here. That's a good thing anyway. All right. So question. All right. Any question? Okay, then let's start. This is fairly easy and quick lab actually, because the first part is nothing much, with just we recording the background radiation and then radiation count, different type of radioactive sources. And then the second part is actually try to understand the unknown source, right? That also there's no calculation or anything. Only simple calculation is actually for this one, okay? So this graph, we can do it easily. After we do the graph, we can get the slope and identify the lambda. If I know lambda, I can calculate the t half. T half in this barium case, we expecting about like 150 seconds. We may not get that exactly. That's totally fine. But if we get within like certain low percentage error level, we are fine. Okay. So that's the plan. That's the only simple calculation. We have 2 grams, this calculation, everything else just a table. After you finish I will keep this link open since we're not doing the lab report till maybe end of this week. You don't need to submit the data sheet immediately tonight, okay? I will keep it open maybe till Saturday, I think that's fine. Saturday night. If you need more time, just let me know. But I think nothing much to do after we record everything. You just to finish up the answers for these few questions. I'm not going to discuss those questions. You can read those quick answers, not in the lab manual directly. These are some of them are general questions. Okay, I did not put the description for the lab manual because that description available in the textbook and elsewhere. If you just Google it, you can find it very easily. Just for the knowledge base. Okay, nothing else otherwise. So for the knowledge base, what is the alpha particle, what is a beta, what is a gamma radiation, what is the nuclear fusion, what is the fission, those answers you can find easily. Okay, don't copy paste anything directly, just read it and then write it down in your own words. Okay. All right, then let's start. You can click the link on page number 2. So that will that should bring you into this page. That's our simulator. Where is looks exactly similar to the in-class setting. Actually, that's why the simulator is nice, because this is how exactly look like. There's a stand right here. Usually that part is not visible here. You can put the tube on that stand. Then you can put the source right here underneath on the table. Okay. And then this is connected to the counter. And whenever the radioactivity happen, that Gauge counter can tell you how much radioactivity happened within the given time. In this particular simulator, you can see on the top different options, right? Radiation source. I can change that into background alpha, beta, gamma, unknown, barium 137. So that's the way we're gonna proceed slowly. And then the barrier means I can actually put the detector after applying the barrier material. Like for example, if I want to apply the cardboard, you can see several number of cardboard appear here. So it's going to be underneath here and the cardboard on top of that. I can select how many cardboard layers I can apply. So we can measure each, multiplying each layer at a time, but it's not really anything important. We can take at least 3 readings by changing the number of layers, okay? And we can get rid of that for the moment. And then count duration here, we can select either 10, 30, or 1 minute. But if this is a real Geiger counter in like the in-person class setting, then the Geiger counter actually has the setting called timer doesn't working. We can actually see the count continuously. So that continuous mode is the one we need if we're doing that barium half-life, because if I go every 30 seconds, for example, then after each 30 seconds, I have to click the start button again. So during that, certain amount of count going to be lost. That will be one of the error we're going to see after we do the time T half. Okay, but but anyway, with the simulator, there's no continuous mode. Because of that, when we do the last part, first 2 sections are fine, nothing to worry. But when you do the last part, we would like to get the count every 30 seconds. That's what we needed. But when we recording it, in between we should not pause, because we're going to lose amount of counts, right, during that pausing and then switch on. So that stopping and then starting again, we have to do manually. So that's going to lose a little bit of count, but that's, I think it's not big deal. I tested earlier, the number we're getting for the T-half is reasonable. So other than that, it's that's all. Then we can do the first part with the 30-second count. 30-second count mean after 30 seconds done, counter will stop automatically. Okay. Let's do for the background, for example, to get practice. All the right here on the right hand side options we don't know, we don't want really. We can use the timer if you want to, but we don't need it. The reason why we don't need it, because if I select the right here 30 seconds, it will stop automatically after 30 seconds, the counter. Okay, so we don't need that timer anyway. Other options we don't need, we just need to start. Now it's background, there's no sources, but you can see still it detects some radiation. So the background actually has the radiation all the time. That's why generally generally you heard, I think if you do the long distance air travel, the flights are usually flying around 30 kilometers high region, right? So if you go really above the ground level, in our atmosphere, actually we exposing to very large amount of radiation. Generally, there's no radiation shield particularly, but there's a shield anyway because outside cover and everything. But there's no specific radiation shield in the normal air flight. So we're going to expose anyway more than, I think, several of dental X-ray level radiation. Definitely, maybe I don't know the number, somewhere I have seen they compare that amount of radiation we exposing during the long distance air travel to the amount of radiation we getting with the dental X-rays and then so on. Okay, you can read those information for interest. Okay, So you can see the number of count is 24. Now keep track on that number because that number is going to change into like thousands if I have a really strong radioactive source right here. Okay. So let's start working on table 1. So now the radiation source is background. So the number of cardboard is right here. I did with without any. So we'll say we'll do with 1 cardboard because I have only 3 lines. Set it here. Can do a number of cardboard 0 and then 2 other with the cardboards. Okay, in this case, number of cardboard 0, amount detected is about 24 counts. After 30 seconds, let's do only 2 values with the barriers added. Okay, let's add cardboard and let's do maybe 3 layers or maybe 2 layers. Okay, it doesn't matter, we're going to test only 2 of them. So let's do 2 layers of cardboard and then let's repeat this experiment. Count again. It's going to stop automatically after 30 seconds. That's why I did not switch on the timer, but you can switch on if you want to, doesn't matter. It's nothing, anything different, right? 22. And let's try with maximum number of layers. We can add maybe 5, right? Let's try with 5 layers. All you have to do, change the number of layers and the number of barriers and then click start. Then after 30 seconds done, it will stop automatically. There's no effect, right? So because it's a background, because anyway, background radiation hitting the Geiger counter anyway, even the barriers are there or not, right? 26. And let's try this with different number of barrier materials. So right here, you can see when I make in the table, I just copy paste this one. As a result of that, the same names repeating. But the third column right here should be our second barrier material. We'll use the plastic, okay? So you have to change that into number of plastic. Number of plastic layers. Let's do that with the 0. Actually, I can't do that. I can, right? Let's do that with none. That's going to be about the same number, but you can see the radiation is completely random. It's not really anything consistent, right? I may not get 24 at all, like I got for the cardboard. When I did cardboard 0, I got about 24. So I may not get 24 at all. I will get a different number. So now I get in 23. So it means it is consistent, right? So now meaning it's repeating again. Let's try this with 1 plastic layer. 1 plastic layer. And then we can take 2 more data points by increasing the plastic layers to see whether there's any effect. It might not. The reason is background radiation is anyway detecting by the Geiger counter whether the layers are there or not. This will be affected only if I have a source right here. If that source is blocked by a certain barrier, then that will be visible. Okay, that's what we try to understand in next few steps. It's about 22, nothing much changes. So let's do maybe 3 layers, right? You can do all all five if you want to like go one by one layer, two layer, three layer, four layer, and five layer. Doesn't matter. So we're not really anything quantitatively calculating or anything there. This is just like qualitative estimation to see how that amount of barrier layers is affecting. Okay. After it's done, it will automatically stop. Then you will see these are highlighted. Right now it's not. Right now it is stopped. It's about the same, right? 25, which means it's a background radiation. Doesn't matter how many layers I actually put there. So let's do again with the 5 layers putting there. Now in the next step, you will see the effect of these barriers when the source is actually underneath. Okay, that's the idea, because the background radiation is everywhere. Because of that, whatever the number of layer you put here doesn't matter, because Geiger counter gonna be Geiger tube gonna be detected anyway. So you can see it not anything affected at all. 5 layers. Just repeat this, because if you're doing the background radiation, usually we have to repeat it at least like maybe 10 times to get the average background radiation, because you can see that number changes, right? Changes 22 to 24 to 25 and 26 sometime, right? It's about like some 20s, but we don't know exact numbers. Because of that, we have to repeat the measurement like many times, then get the average usually. Because if this background radiation is much higher, then later when you do the last part, we may have to subtract the background radiation. But generally, our background radiation is extremely small number compared to the real radiative sources. Because of that, you will see later this number is almost negligible. Doesn't matter that number at all. Okay. Let's try with maybe number of layers of lead. That's the other option we can do. Can do with the lead 1 layer and then 3 layer and 5 layers. Okay, that also you have to edit that lead layers 1. Okay, so 18. That little bit detectable now, right? Change is fairly reasonably high compared to other one. Let's see whether that gonna change with the layers. Okay, because lead is very heavy element, so that can actually block huge amount of radiation comes in. Let's take a look. Nothing much, because still it's a background, right? You can see that number changing to 24 now. So I have 3 layers, 24. That's keep track on that. You can see that number is actually almost consistent for the background. But if I have a source underneath, that should be able to tell us whether the layers is actually effectively blocking the radiation or not. Okay. So this information we're recording here will be very useful when we're doing the next part, okay, with the source putting underneath. Let's record that with the 5 also, because that will be important when you're recording next. Especially important when we try to identify the unknown source. 22. Okay, so that means the 5. Now that's the background. Now if you look at the background is almost very consistent. If I take the average of all this radiation, I can calculate the average background radiation. Average going to be around somewhere 20, 22 or so, right? So we may not need that number to reduce later because you will see amount of count detected when I have the source going to be very, very large number. If that number is like some 1,000 value, then reducing this number not going to be doing anything, right? So if that number is like maybe 100, then this 25 going to be very, very important. We have to reduce that properly because that's background radiation always there. So if I detecting the source radiation like 120, then the real number of the source radiation going to be 120, not the 120, 120 minus 20. So it's going to be like about 100, right? Counts per 30 seconds. So let's do with alpha source. Okay, so let's go back to the cardboard, none first, and then let's do alpha source without any barrier, and let's count it. You can see now how much faster the count rate varies, right? Count number varies. You can see count rate. If you do for 30 seconds, that's going to be a very large number. See now that number is like some thousands of value. So which means the background radiation almost negligible. Okay, that's the idea. You can see per 30 seconds, I'm detecting without any cardboard about like 1573. So by comparing that with the previous number right here, without any cardboard, without any barrier, just the real source radiation, you can see the background radiation almost negligible. That's what I mean earlier. If I do any calculation, I have to reduce the background radiation. But generally, if this number, since that number is too large, reducing 24 not going to be doing anything is anything at all. Okay. All right, then let's try with applying cardboard layers to see how it's going to respond. We'll do the same numbers we done earlier, then we can compare easily. Okay, 2 cardboard layers. Let's check again the alpha radiation. You can see speed decreases a little bit, right? Even for cardboard, which means the even cardboard can actually reduce amount of alpha radiation by large. You can see number is not increasing the rate it increases earlier, it is actually much slower increment, right? Okay, 224, you can see it decreases by large, right? Just putting the 2 cardboard layers. Now the amount of count is 224. So if I do 5 layers, let's see how much it can detect. Let's do 5 cardboard layers. Now you can see background radiation always detecting, right? It's everywhere. But if I have the source just underneath that cardboard or the barriers, then that actually preventing the radiation coming from the source. Okay, that's what we generally call the radiation shield. Okay, now it's 43. You can see it's like twice the background radiation almost, but compared to the real source radiation rate, like about 1573 counts per 30 seconds, compared to that number, like even couple of cardboards can completely block alpha radiation without big problem at all. So let's check this radiation shielding with the other possible sources. I can do this with the plastics and the lead, right? You can just copy paste the first one if you want to directly into next few layers, because I think I did not update that correctly. So let's try with the plastics. Plastic, let's apply same numbers we done earlier table, 1 layer, 3 layer and 5 layers. Okay. Plastic 1 layer. Look like about the same as the cardboard, even looks maybe cardboard is better probably. Yeah, the real source value is 1573 by applying one plastic layer that dropped to like 262. So the huge block 262. And then let's try with the 3 layers. About 31. So that actually much better, right? So now it's about 31. So let's try with 5 layers. You can see now the density of that material we are applying is the key, right? If that is a very dense medium, it can actually block the radiation by large. Five layers, drop it into like about 30. Not much difference like compare with the cardboard and plastic. You can see it not really big difference. If there's a difference, definitely you can see 5 layers cardboard and 5 layers plastic slightly lower, but it's not huge difference compared to cardboard. Let's try this with the lead. Then we should see maybe a big difference there. So let's try with lead 1 layer. Now you can even detect that the speed or the count rate increment is not really strong as any of the previous numbers, right? This layer thickness is actually not given in the simulator. It should be about few millimeters. That's what my feeling. Maybe like 1 millimeter or so, maybe 2 millimeter layer thickness. If you do this in class, we have these layers. Those are like, it's very, very tiny, okay, very thin. You can see lead 1 layer can actually almost lower than the 5 plastic layers. So that's the idea. So the lead is very, very heavy element. So the density is very huge compared to other two barriers. So lead is actually really good source to block that, right? So if I do maybe 3 layers, it can fully block. Now it is in the range of the even with the one lead layer in the range of the background radiation almost, because background radiation once we got about 26. So this number is almost the same now. Let's try with 3. 26, almost very similar to the background radiation. And let's try with 5. I think I have to go back and change this into 5 layers. Usually, if we do this in class setting, the counter has to be reset every time. There are certain things we have to do in terms of before taking any measurement, because the previous number there, if I let it count, it's gonna count on top of that. But the simulator reset automatically. Okay, there's no reset button. Whenever I click again, it will reset again, counting from the zero always. Now it's about 23. So, which means even the one layer is good enough. There's no any difference between one layer and 5 layers in the length. So it technically completely block. This is actually the background radiation. So that's the idea. Let's check with these other two non-radiation, beta and gamma. Then we'll try to identify the unknown radiation. Okay. Any question? Let's try with first without anything. 30-second beta. Type of barrier should be none. Okay. You can see that count rate is much faster, much faster even than the previous one. So I should get the without any barriers total number of count should be some thousands of value. One 175. Earlier I got 1573, right? 1175. Let's try with 2 layers of cardboard to see how it reacts, how it affect for this particular case. Beta radiation. Not seems to be nothing much. Beta radiation seems to be passed through the cardboard without any problem. You can see earlier alpha radiation blocked by even the cardboard by large, but the beta radiation seems to be not much affected at all by the cardboard. It's affected little bit, 958, but nothing. And let's try with 5 layers of cardboard. Six 668 now. Even the cardboard actually affected. It it definitely affected, but it's not much affected than the alpha source, right? You can see alpha source, the 5 layers almost like reduce the number very close to the background radiation value, but the beta radiation, even the 5 layers doesn't do much. Okay, it reduce compared to the 0 layers. It reduce much, but not anything really effective at all, right? Let's try this with the plastic. 3 layer and 5 layer. Okay, technically we should do all those numbers to really see how this sensitivity changes, but I thought that it's not really much anything meaningful since we're not doing anything like analytical calculation or anything. This is like something like qualitative observation. So I thought that to reduce the number of repetition. Okay, but you can report it if you like to repeat that. Okay, 492. Now you can see plastic actually can reduce much. We have seen that earlier too, right? So the plastic is much denser compared to the cardboard, right? So the plastic one layer almost reduced into now 492, almost half of this value right here, more than the twice the cardboard value. Let's try with 3 layers of plastic. $126, that is actually very much effective. So let's try with 5. $41. So that actually very much effective. That almost very close to the background number, right? So let's try with the lead. So lead is very, very heavy. So we should see that effect here. About 69, very less. Let's try with lead 3 layers. Almost it should cut down to like 0. No, not 0, the background number. You can see if the technically actually even 30 seconds is not good enough. We have to count this little bit further long time, maybe 1 minute, and then take the average out of that. That would be better, but I think the 30 second is fine. So about 19 with the 3 layers. Now it cut down by large. And then let's see with the 5 layers. It's almost now at background number. Should be just the background value, right? Should not change at all. About 26. So that both of these numbers, after 3 layers, it's almost at the background value. So let's check with the gamma also, because we need that data to see the identify the unknown source. Okay. So let's check with the gamma without any barriers. 30 second again, without any barriers. 2032. So that's the largest value we got compared to any of the previous. Let's try applying the barrier slowly, maybe cardboard 2 layers. Seems to be there's no effect at all. (1972), almost. There's little bit, only very little effect. Let's try with 5 layers. Quite interesting. It's the same number almost, 1978 actually. Almost no effect after maybe 1 layer. That means the cardboard layers. So let's try with the plastics. 1 layer. 'Almost similar to the cardboard, nothing much. 1863. Slightly less, but nothing much, I think. But let's try with the higher number of layers. Try with 4 layers. (1676). Try with 5. Oh, I did try actually earlier with 4, right? That's not a good idea because we should have the same numbers to compare actually next. I have to repeat that again. Since I'm not reporting all the numbers, number of barriers, we should report only the same numbers we report earlier. Then when we do the unknown material, it's easy to compare them. (1684). Try with 5. (1667). So which means after about like maybe 2-3 layers, it's also not anything much useful. Let's do with the lead. 1 layer of lead. Slightly less compared to the plastic, but not much. 1484. Try with 3 layers. 840, that very much effective compared to all the other, right? That's what we expecting because lead is very heavy. Check with the 5 layers. $510. So that actually very much effective, but still you can see even for gamma, because gamma is actually the highest energy radiation. So that that tells you that the effect is actually much heavier for the other two. If I have a lead 5 layers, you can see it can fully block alpha, beta, both radiation, but gamma, it seems to be not. Okay, it reduced by about maybe 1/3 to about 1/3 of the original value, maybe 1/4 of the original value, but not really, cannot fully block that radiation. Okay, let's now, these numbers, why we recorded it, it actually not to identify that amount of activity, but we need that number to identify the unknown radiation. Now, after you record the unknown radiation, record it for the same values without any barrier, 2 reading for the cardboard, 3 reading for the plastic, 3 reading for the lead, then you can compare that numbers with the numbers above to identify what that source should be. You have to write then a discussion about how the radiation shielding with the different material, what you actually learn about the radiation shielding with the different materials, and then how you identify about the unknown radiation, that you have to write it down right somewhere here. Okay, so you can add somewhere here how you identify the radiation method, just like a couple of sentences. We're not doing the lab report, you don't need to write a huge large paragraph or anything. So let's do unknown without any adding any barriers. Maybe we can identify that directly comparing that number with the previous 3 values without any barriers. That may be good enough actually to identify if you see very close numbers to those 3 recorded values. Okay. Activity is much higher compared to the background radiation anyway, now already thousands. 1136 now, it definitely not gamma, maybe close to beta. This is 1573 alpha, right? It seems to be very close to the beta radiation. So it should be beta. Then what you have to do now, by looking at the 0 barrier value, I can guess that should be a beta radiation. But to confirm that, what you have to do, check how it is sensitivity changes by changing the barriers, plastic to lead. Okay, so that's the way. Now let's record this one, 1136. Add the cardboard 1 layer and then see how the sensitivity changes. If it is really beta radiation, that should be, sensitivity value should change about the same numbers as we did earlier. Okay, 2 cardboard layers. Same numbers you recorded earlier, because that's the easy way to identify. I think, yeah, because the beta radiation we got with the 2 layers of cardboard 958, now I am getting 950. So it should be definitely a beta radiation. We don't need to repeat all, but let's repeat all to make sure beta radiation. Okay, let's repeat with the 5 layers of cardboard. About 680, I got earlier 668. That should be very close. Try with plastic one layer. Four six eight. I got earlier 492. Close. Very close numbers. Let's try with 3 layers of plastic. One or two, 126 I got earlier. Very close. Try with 5. Mistakenly click this one, but hopefully it will not affect. Let's see. Should cut down all the way to the number close to the background radiation. $39, $41 earlier I got. That's a good number. So you can write that information which I mentioned earlier, the how you get this value right here on the top. Just you can expand this row. Just click and drag right here and then expand it. And then if you are on the Windows machine, if you do Alt and Enter, you can bring the cursor into the down. Then you can explain how you find it. Okay, explain how you find the unknown source. Okay, technically just you have to tell how you compare those numbers, just one or two sentences, that enough. Okay, try with the lead also to make sure. One layers. 67, exactly same. We got earlier 69. 3 layers. We earlier we got 19 actually with 3 layers, but we are getting 33 here. Maybe my earlier reading I have to check again to make sure. Let's see. Let's continue with the 5 layers. That's the only very different number I saw. That almost like very different, almost twice, but all the other numbers are very good match. 26, I got 29 earlier. I think it's fine. Only that particular data point. I may have to repeat probably this last one for beta radiation again. Otherwise, it looks fine. So it definitely a beta radiation. Nothing much to do at all. Just write it down one or two sentence how you identify that, okay, by comparing the data. So any question? Okay, then let's move into the next part. Radioactive half-life. Now you know the idea. Half-life mean when we start in detecting that radiation, we're going to detect certain amount of activity. So the half-life is actually the time it took to reduce that amount of activity by half. Okay, that's the idea. So let's to do that, I have to detect the continuously, but that continuous mode is not available here. We're going to detect the activity per each 30 seconds, and then we're going to continue that, repeating that measurement again and again after we put the barium 137 source, at least maybe 10 data points or so. Okay, if we have 10 data points, that should be good enough. Time we'll measure in terms of unit second. Activity we measuring per second, right? This is actually count per 30 second. So the unit gonna be per second, and the total count also gonna be then per second. And the ln, n is just a count, right? We don't need the unit actually for that one. So the count for 30 second we'll convert into ln. So let's now, to do that, we need the barium source, right? Barium 137, that's the barium source, and then get rid of all the barriers. None. Do not apply any barrier. We need to record the full activity as accurate as possible. So we'll record this each 30-second intervals. And all I have to do, you can click the new barium source if you want before you start. And then all you have to do, click the start count and then wait 30 seconds. After 30 seconds done, you have to continue without delaying. Okay, minimize the delay as much as possible. So the amount of count after 30 seconds. $29.68. Click start count again, record that $29.68. Okay, now we're going into the next. Then it's going to be 60 seconds, right? $26.18. Then immediately click start count again. Okay, now we're going into a next 30 seconds, but the time is continuous. Okay, that's what I mean earlier, because after you activate that source, if the source not going to wait, right, until you click, source going to continuously emitting the radiation. So then we're going to lose amount like maybe 1 or 2 seconds between that clicking again, but that should not be a problem, I think. The timer, we can set it up later. We'll record these numbers first, okay? Try to minimize the timer delay 2240. Click start, record 2240. $18.74. 1594. Also, there's no unit for count, right? It just number of count are after that particular time period, right? There's no units for the count. What, 1447, 1215, 1075, 931, 810, 734, 12, 543. So that should be good enough. I think we have more than 10 data points. So let's record the time each. This is after each 30-second, right? So you just need to add the first cell with another 30-second. Then if you click and drag, it will automatically correct the values, okay? So you have to do second cell right here. Instead of typing 60, just type B36 plus 30. No, if it is going up and down, these numbers, it's completely wrong. Okay, they should show you activity decreasing consistently by large numbers. Okay, so you have to redo it again. Always click the new barium source and then start again, and it should show you consistent decrement. If not, it's completely wrong. There's no meaning analyzing that data. And if you're recording this in class, actually we're not going to see these values directly. Instead, what we actually gonna see in continuous mode is the total count, right? Let's take a look. This is not needed for our analysis, but this is how it's gonna look like. If we're recording this in class, after 30 seconds, we're gonna record that number. Then after another 30 seconds, you're not going to see this number. Instead, what you actually seen is this number plus this value. So you're going to see this number after 30 seconds. After another 30 seconds, you're going to see this number, 7,826, and then 9,700, 11,000, and then so on, because we're going to record this on continuous mode. Because that is much accurate. The amount of error happening during the recording, I think about the same anyway, because one person has to tell to another person to record it. If you're trying to do it alone, then you have to look at the counter and then record it. It's going to take a little bit of reaction time anyway. It's the same as what we're clicking here. So I think it's going to be the same amount of error. So that's the number we're recording in continuous mode. Then you have to extract these numbers from that. Okay, this is the number we need to do the analysis. Okay, that is the number of count after each 30 seconds. As the time passing on, you can see activity should be decreased. That's why this experiment we can't do if I have a source which is the half-life is thousands of years, then I can't do this experiment because the activity doesn't change within few seconds. Okay, so within 30 seconds you're not going to see any difference at all. So that's the idea. We'll take a quick break and then we'll start in a bit. Okay. All right, so the graph one, just to observe the behavior of how the count rate decreases as a function of time, right? So x value should be time. So x value should be time, and the y values should be the number of count. Okay, you can see the shape is exponential decrement. Okay, count versus the time. But the second graph, we need actually time, the ln versus time. Okay, so let's make another graph. Insert, double click, select data, and x values should be time. Y values should be then ln. Click OK, click OK. Now, if the graph is correct, you should see negative slope. Okay, that's why earlier I immediately identify negative slope is not there, then my axis flipped. Okay, so you have to take a look at that. And also you can see graph is on the very top half of the page, which is not good. You can change that by changing the axis scale on the y-axis. Maybe you can change the starting point, double click. Then right hand side format axis, last icon, axis options. Starting point of the y-axis you can change to maybe like 6. Yeah, now you can see the graph is nicely expand throughout the page. Okay, that's how the graph should look like. And as usual, if you have a graph, I need the axis title, and also we need the trend line for this one linear. This one gonna be then ln versus time for barium 137. X-axis type is just time, unit second. Y-axis is ln, and the trend line, I have to have the equation visible, right? Just double click on the trend line right hand side, format trend line options, click the last two, but don't click the intercept because that we can't say intercept into 0. But if we want to identify the crossing point exactly, you can actually extrapolate the graph because we would like to see the y-intercept point. So you can extrapolate the graph to see that crossing point actually. That would be nice. We can go backward maybe like about 0.2 to see. You have to put a little bit larger numbers because that is on ln. So if you put about 100, you can see the crossing point on y. So we can do like 80. Too much. 60. 40. Yeah, that's better. So then you can see exact crossing point, right? You can extract the number from there, but we don't need to because we have that number here on the equation. Okay, we'll use the equation. And that's the graph. Any question? That's the same linearized graph which you have above. Okay, there's no difference at all. We're just manipulating the behavior of the graph to see the way we would like to see. Okay, that's all. So this is going to be then figure 3. It's going to be ln versus time for barium 137. Okay, any question? All right, then let's continue into table number 3. Table number 3, just the analysis part. Okay, slope of the graph, which is 0.0047, negative 0.0047. If it shows 0, which means I don't have enough decimal places there, right? So you may have to reformat everything here on this table, highlight format cells to about like maybe 4 decimal places. Then it should show you the number correctly. And then since we don't have a separate place to put the units, you have to put the units on here, okay? This is ln versus time, so the unit going to be 1/second. So you can report the unit here. 1/second actually is for the slope because it's y/x, right? And the decay constant we can find from the slope. Decay constant is actually slope of the graph. But according to the equation, slope of the graph negative, there's a negative sign in front of the decay constant. Because of that, decay constant going to be 0.0047. Okay, that's going to be per second again, the units. You have to record the units on this cell right here because there's no separate place to record the unit. Okay, should be per second. Intercept of the graph 8.1231. 8.1231. That is, there's no unit, that is the number of activity when the time equals 0, right? What intercept of the graph is actually tells you n when the t equals 0. You can add that information here, n when time equals 0. Okay, that's what the intercept actually tells us. That is the activity, but that is the ln value. Okay, that is the ln, not the n. But from there we can find the n if you want to. You can take the inverse. Okay, inverse ln. Ln n when t equals 0. And starting n you have to find by using that number. Okay, so that's what it's asking here. So by using that number, you can find the starting n. If you know ln n, the number, then you can find what is the starting activity should be. And then let's calculate the half time, t half. For the experimental t half, is actually, you know, 0.0693 divided by the decay constant, right? So this is going to be equal sign 0.693 divided by the decay constant, getting about 147.4468, but the expected value is about 153. Okay, so that's the expected value or known value. You can record that number here directly and add the units. Unit is second for both, right? This is how many number of second it took to go from a starting number. You have to calculate this number because you know the ln value. So that tells you how much time it took exactly to go half of that value. Okay. And then compare that. I'm getting 143, expected value about 150, 53. So it should be good enough. And then this one, I don't need actually this many decimal places. So you can reformat this into like maybe 1 or 2 decimal places. That should be good enough. Let's compare it. Equal sign ABS parentheses expected 153, calculated 147, divide by expected 153, multiply by 100. About 3% error. So that's not bad at all. Okay, question. No questions? Okay. So that's it about the experiment. We have actually maybe half an hour or so, right? We have about like 40 minutes. We can go and take a look 1 or 2 questions from the last chapter. So that's about the experiment. This number also you can calculate. Just you need to take the exponential e to the power of this number, right? So that we can say, let's see what is the function is. So x function, forget the natural log inversion, you have to take a look, otherwise you know how to calculate that one, right? I forgot that function. Take a look, what is the function to get the exponential? I think exp uppercase. Yeah, exp, let's try that. 3371, that should be the starting activity when the t equals 0. That should be correct, because after 30 seconds we record it as a 2968, so that should be fine. So that's the idea. Okay, so this no meaning recording any decimal places here. You should get rid of the decimal places completely from there. Okay, no meaning recording that decimal places there. That's the starting activity. That means when the t equals 0, when time is 0. Okay, so that's about this experiment. We can stop the experiment from there.